Welcome to Brain Vision.
The first step to doing this problem is to draw a force diagram. If this is the box, the worker is pushing on it with a force equal to capital F. This is what we want to solve for in this part of the problem. We have an upward normal force. We have a downward force due to gravity of mass of the box times gravity. And we have a friction force of the box pushing it backwards. Now, applying Newton's second law in the y direction gives us 0 since there's no acceleration in the y direction. This implies that the normal force minus the mass of the box times gravity is equal to 0. I have a minus sign here because it's going in the downward direction, which is the negative y direction. This means the normal force is equal to the mass of the box times g, which is equal to 16.8 times 9.8, which is equal to 164.64 newtons. Now that's not the answer yet, but that is an important piece of information. So now that we know the normal force, we can calculate the friction force in the box, which is defined to be the coefficient of kinetic friction times the normal force. We're given the coefficient is equal to 0.2. We multiply this by 164.64 to give us a friction force of 32.9 newtons, roughly. Now we're going to do Newton's law in Newton's second law in the x direction. In this case, the acceleration is still 0 because we have a constant velocity. And so we're able to set this equal to 0. This implies that F, since it's moving in the positive x direction, is positive, minus the friction force on the box is equal to 0, which means our applied force is equal to the friction force, which we found was equal to 32.9. And so our applied force has to also be 32.9. And that's the final answer to part A. In part B, we remove the force that we're exerting. And so the force diagram now looks like this. We still have the normal force and we still have the gravitational force. And we still have the same friction force. But we're missing the applied force. So if I do Newton's second law, in this case, I can't set it equal to 0 because now it's going to be accelerating. It's going to be slowing down. The sum of the forces in the x direction are just negative FB. And so I know that this is equal to that. And this allows me to solve for the acceleration. It's negative 1.96 meters per second squared, which means it's decelerating at 1.96 meters per second squared. So now we can use a kinematic equation. Let's write down our knowns. We know the initial speed is 3.5 meters per second, which is just given in the problem. We know the final speed is at rest, so 0 meters per second. We know the acceleration is negative 1.96 meters per second squared, because that's what we calculated here. And the unknown we want to solve for is the distance traveled. Note, we also don't know the distance, but that's not our true unknown. So we're going to pick a kinematic equation that doesn't involve distance. And so the one we're going to use is this one. Right there. Solving for x minus x naught gives v squared minus v naught squared over 2a. At this point, we can plug in all our knowns, and when we solve for it, we get 3.125 meters, which is the distance that the box travels after the force stops being applied, and that's the final.